All right, so last time we finished Chapter 13, came in, got some few questions over Chapter 13. I'm located on page 333 of the Hine textbook there. Anyway, so number 29 is one of the ones that was asked, and here's what it says. It says that as if 75 grams of ice at 0 degrees centigrade were added to 1.5 liters of water at 75 degrees centigrade, what would be the final temperature, that's T sub F, of the mixture? All right. So, how would we go about doing that? Did anybody look up and look up how to do this one or work on this one at all?
Do you have to change the liters? Can you keep it?
No, you're probably going to have to change the liters because I think what we're going to have to do here, and I certainly haven't worked the problem, but here is the water, okay? Now I want to change the water to mass, so that's 1,500 grams of H2O, okay? And then what you're going to do is you're going to take this hunk of ice right here, and you're going to put inside of that water. And it wants to know what the final temperature of water would be. Okay. Now, I'm going to be honest with you. I really don't know where to get started. I mean, it don't happen too often, but I really don't, so I'm going to have to play with this in just a minute here. Basically, we're going to have the heat of the water equals the mass of the water times specific heat of the water times the final temperature of the water minus the initial temperature of the water. And then we'll have the heat of the ice equals the mass of the ice times the specific heat of the ice times the final temperature of the ice minus the initial temperature of the ice. All right. Now, let's deal with the ice first, I suppose. And here's what we got. What's gonna be negative, the ice or the water? The water, right? Because that's what heat's going to be leaving. So that's negative Q sub W equals plus Q sub ice. So what is the Q sub ice? Well, the mass of ice is 75 grams. What's the specific heat of ice? We did it last time. It was 2.00 something. Does anybody have their notes? 2.00. 2.092. That's a specific heat of ice. And that right there, of course, would be in a table. Now, the final temperature of the ice would be what? 0. Minus the initial temperature of the ice is 0. So all that's going to be 0. And that don't look good. Well, what is the final temperature of the water? Oh, you're right. So the final temperature here would be X, right? So that's going to be basically 0 plus X plus 0. All right, well, let's see what that's going to do for us. We're certainly going to check this one in the solutions manual, right? It's one of those starred problem deals. Okay, the mass of the water is 1,500 grams, 4.184. Final temperature of the water, just like she told me, that's what we're looking for. Initial temperature of the water, 75 degrees. So let's see here if we can find out what that final temperature of the mixture will be. Does anyone in this room have a solutions manual with them? You've got one? All right, bring it up there. 75 times 2.092. is going to be 156.9x. 1,500 times 4.184 is going to be 6276x minus 470700. I want to combine the like terms, so that means this is 40 70700. Subtract that to the other side at 6276 minus 156.9 is going to be 6119.1 x. Now, 470700 divided by the second of the answer will be 76 degrees centigrade. That's what x will be, and there ain't no way. That would imply that water heated up. What's going on?
Don't you need to compute it in 2 separate steps to compute how much energy it takes the ice to melt, and then after the ice melts, do another step because the specific heat changes?
Ah, the specific heat changes. Okay. Well, this is no good. And again, you know, I'm really glad that I make these mistakes and I'm talking through it, because if you were on a test and you did this, it's important to know you're wrong, which I'm wrong, right? I mean, obviously, you cannot put ice in something and temperature go up. That ain't going to work. All right. Now, what do you want to do? You want to take, he wants to work with ice first, and he wants to figure out how much energy it takes ice to melt.
Yeah, the 75 grams.
So he wants to take 75 grams times the heat of vaporization of ice. Is that what he wants to do? All right, so what is the heat of vaporization of ice in the table? 225? 335 joules per gram, right? Grams will cancel, so that means that it's going to take 335 times 75. That means it's going to take 25,125 joules for the ice to melt. Okay. This right here will be the ice melting. Now what he wants to do is concentrate on the water. And what do you want to do with water then?
Negate those joules from the temperature of water.
All right, so you want to take 25,125 equals the mass of the water times specific heat of water.
Wouldn't it be a negative?
Do you want to put a negative here?
I'm guessing.
Okay, he wants to put a negative here. You know, we'll be able to check and see if we're right. He wants to put a negative there. And then you want to do MC delta T now?
Yeah.
Okay, so the mass of water is 1,500. Specific heat's 4.184. Times the final temperature of the water is, we don't know, minus the initial temperature at 75. Does this look good to you? Is this kind of like what you had in mind?
Yeah.
All right. There's nothing wrong with this dialogue, people, back and forth with this, right? Okay, so let's see here. 1,500 times 4.184. All right, so that's going to be 6276x. 6276x minus a negative 470700. Well, that number's coming up again. Okay. So let's see here. Combining like terms, you're going to take negative 25,125 plus 470700. So that's going to be 445575 equals 6276x. So now I'm getting 70.997 or 71 degrees centigrade.
And from there, I would do the dual equations with the specific heat of water on both sides. Because now you have 0 degree water and 71 degree water.
Okay. So this right here is the final temperature of the water, right? Okay. So now what he wants to do is say, now we have two water equations, right? I don't know that we're going to need to do that.